In the context of explainable artificial intelligence, XAI, attribution-based explanations have been widely used to interpret model decisions. However, the literature lacks consistent configurations and systematic investigations, leading to inconsistent evaluation results. To address this limitation, the authors introduce MetaRank, an open platform for benchmarking attribution methods in the image domain. MetaRank assesses 8 attribution methods using 6 renowned model architectures on 4 diverse datasets, employing both the most relevant first, MoRF, and least relevant first, LeRF, evaluation protocols. The benchmark reveals 3 key insights. Firstly, evaluating attribution methods under disparate settings can yield divergent performance rankings, highlighting the importance of standardized evaluation protocols. Secondly, despite inconsistencies across cases, performance rankings exhibit remarkable consistency across distinct checkpoints along the same training trajectory, suggesting that model architecture and training trajectory have a significant impact on attribution method performance. Thirdly, prior attempts at consistent evaluation fare no better than baselines when extended to more heterogeneous models and datasets, emphasizing the need for more rigorous evaluations. The findings underscore the necessity for future research to conduct comprehensive evaluations encompassing a broader range of models and datasets, and to reassess the assumptions underlying the empirical success of different attribution methods. This is crucial for developing reliable and generalizable attribution methods that can be applied in real-world scenarios. In the realm of deep learning, understanding the internal mechanisms of neural network architectures is crucial. This page delves into attribution methods, which aim to generate an explanation map that attributes predictions to specific image regions. However, evaluating these attributions directly poses a significant challenge due to the lack of ground truth. The paper differentiates between 2 evaluation methods: expert-grounded and functional-grounded. Expert-grounded evaluation relies on human annotated importance, which has its limitations. On the other hand, functional-grounded evaluation focuses on assessing how well the attribution method aligns with the model's behavior. The primary objective of this work is to provide a comprehensive understanding of attribution methods and highlight critical problems that need to be addressed. To achieve this, the authors introduce MetaRank, an open-sourced attribution benchmark. This benchmark features rigorous evaluations, comprehensive analyses, and extensive baselines, aiming to set a new standard for evaluating attribution methods in deep learning. Evaluating attribution methods in machine learning models is crucial for understanding model behavior. However, previous evaluation efforts have revealed inconsistencies in performance rankings across different experimental settings. This inconsistency is attributed to 3 key findings. Disparate experimental settings yield divergent performance rankings. Performance rankings exhibit consistency across distinct checkpoints along the same training trajectory. In prior attempts, such as Remove and Debias, fare no better than simple baselines when extended to heterogeneous models and datasets. To address these limitations, this paper introduces MetaRank, a novel benchmark for evaluating attribution methods. MetaRank aggregates ranking results from diverse settings, mitigating biases associated with specific configurations. This enables systematic comparisons among existing attribution methods and provides extensive experiment results. The benchmark is designed as a flexible framework that standardizes experimental settings and simplifies the integration of novel algorithmic implementations. The paper also reviews related work in attribution evaluation, categorizing them into expert-grounded evaluations and functional-grounded evaluations. Expert-grounded evaluations rely on human judgment, while functional-grounded evaluations provide more objective evaluations by comparing model behavior when certain individual features are present or absent. MetaRank facilitates comprehensive benchmark comparisons across multiple settings, providing pivotal insights into attribution method performance. By aggregating ranking results, MetaRank enables researchers to systematically compare and evaluate attribution methods, ultimately advancing the understanding of machine learning model behavior. Evaluating attribution methods in deep learning models is crucial, but existing methods have significant limitations. 2 common approaches, most relevant first, MoRF, and least relevant first, LeRF, are flawed as they violate the assumption of consistent distributions between training and test data. This makes it difficult to determine if the decline in model performance solely results from feature deletion. Hooker et al. Addressed this issue by developing remove and retrain (ROR), which resolves inconsistent distributions by synchronously deleting features from the training and test sets based on attributions and then retraining the model. However, ROR is computationally expensive and thus unfeasible for scaling up. Wrong et al. Discovered inconsistent MoRF and LeRF rankings from ROR, which they attributed to information leakage, and proposed remove and Debias (ROAD) as an alternative. However, ROAD still has inherent defects, such as replacing features with substantial values instead of entirely dropping them. Deng et al. Noted the lack of unified theoretical frameworks for evaluating attribution methods and proposed a Taylor interaction system to unify 14 attribution methods under a common mathematical formulation. However, applying this framework to new methods requires manual theoretical analysis, hampering scalability and efficiency. Recent studies have explored attribution evaluation from diverse perspectives, including comprehensive viewpoints and the consistency lens. However, the absence of standardized experimental settings and systematic evaluations in previous literatures poses challenges for comparing existing methods universally. To overcome these limitations, this work proposes meta-rank, a novel evaluation benchmark, to provide a comprehensive evaluation of attribution methods across multiple settings. The benchmark considers 8 prevalent attribution methods: saliency, input times gradient, integrated gradients, guided backpropagation, deep lift, deconvolution, LRP, and guided grad-cam. In Explainable Artificial Intelligence, XAI, a general assessment paradigm is formalized through the derivation of key concepts in attribution evaluation. This paradigm is applied to an image classification dataset D, comprising N samples and C categories, where a deep network Y equals F theta, X, predicts Y for input X. The primary objective is to generate a heat map H, assigning saliency scores to each input pixel. To evaluate the performance of attribution methods, 2 protocols are introduced: the most relevant first, MoRF, and the least relevant first, LeRF, strategies. These protocols assess performance degradation by progressively removing the most or least salient pixels, respectively. MoRF measures the impact of removing the most important pixels on the model's performance, while LeRF evaluates the effect of removing the least important pixels. The authors emphasize the effectiveness of attribution methods in identifying significant pixels and highlight the need for a broadly applicable standard across multiple experimental settings. This standard would facilitate the comparison of attribution methods and provide a comprehensive understanding of their performance. The authors draw attention to the inconsistency in experimental configurations used in previous studies on attribution methods for deep neural networks. This inconsistency has led to varied observations and difficulties in comparing results. A table is provided, showcasing various studies, their venues, datasets, models used, and whether they address the issue of consistency. To address this issue, the authors propose a standardized evaluation framework called meta-rank, which evaluates attribution explanations on a diverse array of datasets, models, and evaluation protocols. 4 commonly used datasets for benchmarking are selected: NWPURESISC45, Food 101, ImageNet 1K, and Places 365. These datasets cover various domains such as remote sensing, food image classification, general image classification, and scene recognition, allowing for a comprehensive examination of each attribution method. 6 widely employed convolutional neural networks, CNNs, are adopted to evaluate existing attribution methods: ResNet 18, ResNet 50, InceptionB4, VGG19, EfficientNet_B2, and DenseNet 121. The use of these CNNs ensures an equitable evaluation across attribution methods with a consistent set of evaluation settings. The authors note that most attribution methods are specifically tailored for CNNs and cannot be directly applied to vision transformers, VITs. As such, their benchmark does not take VITs into consideration. In the field of artificial intelligence, The evaluation consistency of attribution-based explanations is a critical aspect. To address this, the meta-rank benchmark is introduced, comprising two stages: test case generation and meta-rank. The test case generation stage combines multiple factors, including datasets, models, and evaluation protocols, to generate diverse test cases. The meta-rank stage consists of case execution, where various attribution methods are applied to these test cases, and ranking fusion, which integrates the rankings to produce a unified leaderboard. The meta-rank benchmark provides a comprehensive view of attribution methods by considering both protocols for evaluation. It involves training multiple models on different datasets, using them as baselines for evaluation. The technical depth of this approach is enhanced by the use of PyTorch as the framework, Atom for optimization, and cosine annealing for learning rate decay schedule. Furthermore, the incorporation of pre-trained models expands the scope of the evaluation, allowing for a more thorough assessment of attribution methods. By considering multiple factors and evaluation protocols, the meta-rank benchmark offers a rigorous evaluation framework for attribution-based explanations in artificial intelligence. The proposed benchmark metric, meta-rank, aims to provide a comprehensive comparison between attribution methods by aggregating ranking results from diverse test cases. Each test case is defined by a triplet of dataset, model, and evaluation protocol. The metric calculates the probability that one competitor outperforms another, converting it into logistic odds for better sensitivity. The performance discrepancies are then transformed into the meta-rank metric, which is used to derive a score for each competitor. This score serves as an identifier for its comprehensive performance, enabling the construction of a unified leaderboard. This section delves into the consistency of attribution-based explanations across diverse settings. It examines the performance rankings of existing attribution methods, encompassing various datasets, models, and evaluation protocols. A key focus is on the meta-rank method, designed to identify superior attribution methods. The authors conduct extensive experiments on meta-rank, probing critical questions such as the consistency of attribution methods across different settings, the performance of the state-of-the-art evaluation method ROAD, and the feasibility of evaluating substantial methods within a reasonable timeframe. This analysis provides insights into the efficacy and reliability of attribution methods, shedding light on their potential applications and limitations. The comparative analysis of 8 attribution methods across 6 models and 4 datasets, utilizing 2 ablation protocols, reveals inconsistencies in their performance at both model and dataset levels. Model-level inconsistencies are evident, with varying performance of LRP, integrated gradients, and guided grad cam across different models. For instance, LRP performs poorly on the ImageNet Inception v4.m case but shows significant improvement on the ImageNetters Net18.m and ImageNet VGG19.m cases. Similarly, integrated gradients and guided grad cam exhibit comparable performance on the FoodRes Net18.m case but display great disparity on the Food VGG19.m case. The Spearman rank correlations among several cases, illustrated in Figure 3, suggest a pronounced weakness in consistency at the model level, with only 2 cases showing strong correlations out of 18. Dataset-level inconsistencies are also observed, with attribution methods demonstrating noticeable performance variations on different datasets. For example, guided backpropagation shows superior performance on ImageNet VGG19.m, but ranks third worst on Food VGG19.m. Only 5 out of 18 cases show strong correlations at the dataset level. These findings highlight the importance of considering multiple models and datasets when evaluating attribution methods to ensure robustness and consistency in their performance. The evaluation consistency of attribution-based explanations is a key focus on page 11, particularly with the MoRF and LeRF protocols. Table 2 presents a UC rankings of 8 methods across different checkpoints, demonstrating high consistency in the ranking of attribution methods as the model converges. This consistency is further supported by the Spearman correlation analysis between MoRF and LeRF, which shows moderate to weak correlations, indicating significant inconsistencies between the two protocols. The necessity of the meta-rank benchmark is emphasized through the use of the road evaluation method, highlighting the class information leakage problem. The evaluation of attribution methods using the meta-rank benchmark is discussed, presenting a leaderboard of 8 methods, with input circled dot operator gradient and integrated gradients showing the strongest performance. The meta-rank score indicates the ability of each attribution method, with the top 3 methods exhibiting more positive performance. The need for a cross-case benchmark is highlighted to ensure robust ranking results, as the correlation between rankings on different cases is inconsistent. The evaluation scheme involves a unified measurement across 4 datasets, 6 models, and 2 protocols, resulting in 26 sets of data. AUC scores are used as the performance metric, enabling the establishment of a unified ranking list for all methods. The evaluation of attribution-based explanations focuses on the consistency of methods across various test cases. Table 4 shows the results, with input circled dot operator gradient being the top-performing approach and deconvolution exhibiting the poorest performance. The input circled dot operator gradient method achieves high scores by elementwise multiplying gradients with inputs, producing stable attributions. Integrated gradients also shows great potential, closely approaching the top-ranked method. In contrast, deconvolution's hierarchical structure accumulates noise, resulting in its low score. The meta-rank score can be positive or negative, indicating superior or inferior performance. The experimental findings demonstrate the comprehensive benchmarking capabilities of meta-rank, effectively addressing inconsistencies across diverse test cases. The efficiency of meta-rank is also discussed, highlighting its time consumption with varying numbers of methods, including the use of GPUs for enhanced computation speed. The authors propose meta-rank as a standardized benchmark for evaluating feature attribution methods, addressing the lack of systematic research in this area. They opt to use the increment metric as the base metric in their framework, enabling subsequent meta-rank assessment and facilitating broader evaluations on novel tasks. Moreover, meta-rank can accommodate evaluations on other dimensions by deriving a ranking list along each respective evaluation metric. The authors acknowledge the missingness bias problem in feature ablation, which arises from removing pixels through masking values in CNNs. They recognize that completely eliminating this bias is challenging, but believe that a more diverse array of test cases can help neutralize it. Future research will explore solutions for eliminating this bias. The scalability of meta-rank is discussed, where introducing new attribution methods to the ranking involves testing on several existing cases, followed by feeding the results into the ranking fusion module to generate an updated ranking list. The time complexity of evaluating a method on an individual case is linear, and the time overhead associated with the process is optimistic. This flexibility allows for the inclusion of any attribution method into the leaderboard at any time. The authors conclude that meta-rank provides a novel standardized benchmark for robust and unified evaluation of feature attribution methods, aggregating relative comparisons between all method pairs across diverse settings and mitigating inconsistencies. Through extensive experiments, they revealed 3 critical insights. Diverse evaluation settings yield divergent performance rankings. Assessment results remain consistent across distinct checkpoints along the same training trajectory. And previous attempts at consistent evaluation exhibit limitations on heterogeneous models and datasets. The refined version of the transcript for the explainer video starts directly with the content, focusing on the key points and technical details from page 15 of the research paper. It provides a comprehensive overview of the list, ensuring technical accuracy and depth suitable for expert researchers and stakeholders. The current page explores various research papers on explainability methods in deep neural networks, emphasizing the need for understanding how models make predictions and the importance of interpretable results. Papers such as Remote Sensing Image Scene Classification and Understanding Global Feature Contributions highlight the significance of feature importance and attribution methods. The concept of shortcut learning and its impact on model interpretability is also discussed. Furthermore, the section addresses the need for responsible evaluation of neural network explanations and the development of synthetic datasets for part-based analysis. The page concludes by discussing benchmarks for interpretability methods and the importance of addressing missingness bias in model debugging. The paper discusses the evaluation consistency of attribution-based explanations in machine learning models. It presents a comprehensive overview of various attribution methods, including LIME, SHAP, and deep lift, and their applications in different domains such as image classification and natural language processing. The authors also delve into the challenges associated with evaluating these methods, including the lack of ground truth and the need for a unified evaluation framework. Key findings from previous studies are highlighted, including the importance of feature importance scores, the role of model interpretability, and the correlation between feature attribution and automatic evaluation scores. Recent advances in this field, such as the development of new attribution methods like RISE and GradCam, are also discussed. The paper provides insights into the limitations and future directions of research, including the need for more robust evaluation metrics and potential applications in real-world scenarios. Machine learning, computer vision, and neural networks are the focus of several research papers, beginning with the impact of residual connections on learning, as demonstrated by InceptionV4 and InceptionResNet. This concept is further explored in EfficientNet, which revolutionizes model scaling for convolutional neural networks by rethinking the scaling of depth, width, and resolution. Beyond architecture, a unified study examines machine learning explanation evaluation metrics, providing a comprehensive framework for assessing explainability methods. This is complemented by papers on neural network explanation, including the identification of input features with predictive information and fine-grained neural network explanation. Visualization of deep neural network decisions is another key area of research, enabling a deeper understanding of model behavior. Furthermore, the Places database is utilized for scene recognition, while the correctness of feature attribution methods is also investigated. These papers collectively contribute to the advancement of machine learning and computer vision, providing insights into the development of more accurate and interpretable models.